Stall spins are one of the leading causes of fatal accidents in the ag aviation industry, accounting for over a quarter of all fatalities. We've created this video to bring renewed awareness of the potential dangers associated with low-level maneuvering and the ag turnaround. It is our goal to provide you, the ag pilot, with some recommendations to help you recognize when your personal margin of safety has been reduced below an acceptable level. We want to remind everyone to turn smart.
Kyle, thanks for that information. That's important information for us to know. My name's Mike Rhodes. I'm chief pilot here at Air Tractor. I've been here for almost 20 years, and I'm responsible for flight test operations here at Air Tractor. I want to introduce you guys to a good friend of ours and also a customer of ours. This is Steve Gustafson. He's from Tallulah, Louisiana. He's been in the air show business and in the ag flying business for his entire career.
Thanks for having me,
Steve,
Mike.
Thanks for joining us. So Steve, since you were a teenager, you've been around the ag aviation community, and you've also been around air show flying. Tell us a little bit about your background, and we're obviously real interested in the ag part of your background.
I started loading airplanes when I was 10 years old. My dad was an ag pilot. He flew Stearmans, travel airs, and then into Stearmans, and then I started out in Pawnees when I was 20 years old, into ag cats, and then into the air tractors to today. We've got an 802 air tractor, and it just flying at the AeroShell Aerobatic team all over the country, from El Salvador to Nova Scotia, Canada. Enjoying life, man, enjoying it.
We're going to talk to Steve today about how to make safe turnarounds in the ag environment. And he's going to bring not only his ag experience in to the discussion, but he's also going to bring in his air show and aerobatic experience, because those two things are very closely related. There's a lot of similarities between ag flying and air show flying. The low-level environment, it's an unforgiving environment, requires a lot of professionalism, a lot of practice. Tell me about some of the differences between ag environment and the air show environment.
Well, the differences are, when you're in ag, you're there to do a certain job. You're there to do to the best of your ability for your customer. And the air show business is more of an entertainment business. But the similarities are obviously what you said. You're in the environment. You're low level. You're close to the ground. And you need to be always wary of that and understand where you are. Situational awareness at all times. Situational awareness in the air show business is very key. You need to know exactly where you're positioned. When we do a maneuver for an air show, we have to be at the right airspeed, at the right altitude, at the center of the show, at the center of the crowd, or be it may where that point is. The Thunderbirds, the Blue Angels have to do the same thing. Ag is no different. You're flying upwind, downwind, crosswinds. So every turn you make, you need to prepare for that and have a frame of mind in your mindset of where the wind is blowing constantly. I can't emphasize that enough.
Steve, the purpose of this video is to help people understand what a safe ag turnaround maneuver looks and feels like. Describe what a safe turnaround maneuver feels like.
First thing, it's a planned maneuver. Before you ever make your first pass in the field, you should have had that planned. And while you're on that pass, you ought to be planning the next pass. In other words, keep the airplane out in front of you. All of us as pilots, all of us, myself included, know what I'm talking about by having the airplane up in your face. And when you find yourself in that situation, not only you're not safe, you're not able to make good judgmental decisions. So you need to have the airplane out in front of you. Never push yourself into an uncomfortable situation. Keep yourself comfortable and you'll keep yourself safe.
Even when you're in the middle of your air show routine with the three other airplanes around you, you've preserved that safety margin, right? Nobody in that group is taking a chance, right?
That's right.
Everybody's acting within their
It's a choreographed
margin of safety.
routine. It's totally choreographed. We've had things happen before, but believe it or not, if you've briefed it, gone through it, planned for it, I hate to say it's really a non-event.
As it should be.
It's
right?
a non-event because you've placed that margin of error out where you can deal with it instead of bringing it in to where there's no room for dealing with that margin of error.
You built in that margin of error at the beginning, right? Let's talk about some of the elements of an unsafe ag turn. Things like uncoordinated flight, misuse of rudder. Help us understand what some of the elements of an unsafe turnaround maneuver are.
You know, if every air track, if you look in the middle of it, says maintain coordinated flight at all times. Well, that's in there for a reason, and it's a very important reason because we're flying an airplane with a loaded wing. It's a loaded wing. And whenever you step on a rudder, be it the left or the right, if you're uncoordinated, you just took some of the lift off of that, whichever one you're pushing on, you just took some of that load off and you just put it on the other side. That is how you can end up in an unsafe situation, and when the airplane does finally break, one wing is flying, one wing isn't, it's going to roll you over on your back. And the direction it's going to go is whichever foot you're pushing on, whichever rudder that you're pushing on, is going to go that way. So Via, if you're in a left turn and you're pushing on the left rudder, it's going to go to the left, which is obviously a bad place to be in an ag plane, or any plane for that matter, if you don't have the altitude to correct the maneuver. If you're pushing on the top rudder, then it's actually going to break and go over the top. Now, obviously, you have to have the correct inputs to control that. But in the environment that we're flying in, you don't ever need to get the airplane in that situation in the first place. Ever. Ever, never, ever.
Steve, let's dig even deeper into what can cause the airplane to depart controlled flight during an ag turnaround maneuver. We all know that drag increases with increased angle of attack. An aileron that is deflected trailing edge down produces more lift and more drag than an aileron that is deflected trailing edge up. This imbalance of drag force is what causes adverse yaw. When we use poor pilot technique during slow flight and try to pick up a low wing by using ailerons, we have to remember that we're also adding an undesirable pro-spin yawing force toward the low wing. A wing that is on the edge of stall might go ahead and stall when the aileron moves toward a higher angle of attack. The unique mission of the modern turbine ag airplane dictates certain design features. It has a heavy propeller and a powerful engine sitting in front of a large hopper, all out in front of the pilot. Forces exerted by the engine and propeller have a lot of leverage on the airframe because of the long nose. It has a lot of leverage.
Like a long sheet of pipe way out in front is going to be sent down the fuselage, and you have to compensate for that.
So the rudder and the fin, their job is to compensate for those.
It's everything.
For those yawing forces, and as the airplane gets slow in a turn, the rudder and fin kind of loses its ability to correct for those yawing forces. As student pilots, we all learned about the 4 left-turning tendencies. Let's briefly review them and talk about how each one acts on our ag airplane during the turnaround maneuver. Torque is probably the easiest for most of us to understand. Sir Isaac Newton said that for every action, there is an equal and opposite reaction. When the engine and propeller turn clockwise, the airframe wants to turn counterclockwise just as hard. During takeoff roll, torque causes the left main tire to carry more weight and therefore have more rolling resistance than the right main tire, pulling the airplane to the left side of the runway. In flight at cruise speeds, the torque of the engine and propeller is resisted by the airflow over the wings and is easily corrected by a small amount of aileron trim. The airplane loses energy and slows down during the turnaround maneuver, and the ailerons lose some of their effectiveness. Slightly more aileron deflection is necessary to counteract the torque produced by the engine and propeller. The next left-turning force on our list is P-factor, also known as asymmetric propeller disc loading. The propeller disc on an airplane that is going through the air in level flight is relatively equally loaded, but a propeller that is going through the air with an angle of attack, like an airplane that is climbing or turning or slowing down, isn't equally loaded. In that case, the right half of the propeller disc generally produces more thrust than the left half, due to the difference in angle of attack of the ascending blade versus the descending blade. Next on the list is spiraling slipstream. A spinning propeller doesn't push the column of air straight aft. It imparts a rotation on the air, and this spiraling tornado hits the rest of the airplane from different angles. In general, the spiraling slipstream pushes on the left side of the vertical fin, resulting in a yaw to the left. When the airplane is going fast in cruise flight, the spiraling slipstream stretches out and becomes very weak. As the airplane slows down, the spiral tightens and becomes a stronger force. Of the 4 left-turning forces, gyroscopic precession might be the most difficult to visualize and understand. Some flight instructors just gloss over this one, but it might be the most important one for us to understand because it's a really powerful force in turbine ag airplanes. A gyroscope is a spinning mass that exhibits 2 basic properties: rigidity in space and precession. The physics of gyroscopic precession says that a force applied to a spinning object will have a maximum reaction 90 degrees in the direction of rotation ahead of the force that is applied. Basically, when we push on the top of the propeller disc, that force is felt on the right side at the 3 o'clock position of the propeller disc. Gyroscopic forces on the propeller are small when the airplane is in steady state level flight, but become large when the airplane is maneuvering. At slow speeds in a steep bank to the left, when the pilot relaxes back pressure on the stick, which is the correct recovery from a stall, gyroscopic forces produce a skidding yaw to the left. By now it should be pretty clear to see that all of these left-turning forces become strong and reach their maximum at high power settings, at high angles of attack, at slow speeds, and while maneuvering. P-factor and gyroscopic precession both produce very strong forces at high power settings, especially while maneuvering. As the airplane slows down in the turnaround, the vertical fin and rudder effectiveness naturally fades, and if flown with poor technique can eventually decrease to the point where the rudder is simply unable to provide enough yawing moment to counteract the forces, and the airplane begins to roll, yaw, and rotate. At very low airspeeds, there is simply insufficient airflow over the wings and tail to produce the necessary control forces to correct for the left-turning forces exerted by the engine and propeller. Remember that steep bank angles, aggressive maneuvering, high angles of attack, low airspeeds, and poor pilot technique are all ingredients for a spin, and most of the time this happens without enough altitude for recovery. All that happens when you're right on the edge of controlled flight, right? That's a slow airplane, and then the uncoordinated inputs when the airplane's slow, that's when you're really stacking the deck against yourself.
Downwind. You know, and I've actually noticed over my years, when people make that mistake, they're doing it with not quite a full load. It's like when they have a full load, all their senses are in place. But once they get down about a half load, or say a third, you know, just under a half, it seems to me that I can do anything with this thing I want to do. I can, if I want to horse it around or rush this turn, it'll be okay. That's not true at all. You need to maintain coordinated flight at all times. And the torque, the prop on these airplanes is way out in front of us to keep the center of gravity.
I think you hit on a really important point with that. There's another factor that influences flight characteristics. The airplane's center of gravity has a lot to do with its stall and spin behavior. At the beginning of the flight, the airplane's center of gravity is fairly far forward because of the hopper load. As the contents of the hopper are sprayed out, the airplane's center of gravity moves aft, its elevator effectiveness is reduced, and its stall spin behavior can become more aggressive and more pronounced. Keep in mind that most ag airplanes are at or near their aft CG limits when the hopper is empty.
Don't be aggressive and start snatching controls around, jerking things and this and that, because you're just aggravating it. It's not going to make it any better at all.
Smooth and steady wins the race every time, right?
Smooth and steady. A smooth and steady pilot, in my book, is a safe pilot, and a better pilot.
And then eventually smooth and steady becomes human nature, right?
Exactly, becomes It becomes part of the way you fly. And I'm not saying there's only one person that's right or wrong, but I guarantee you, to be a good pilot, you need to be a smooth, precise pilot. Not jerky, snatchy, waiting on the airplane. If you're moving the controls so fast that you're having to wait on the airplane to catch up, you're doing it all wrong.
And not only that, that's hard on a human body after an 8 or 9 or 10 hour day.
Trust me, if you survive through it, you're going to finally at the end of the day go, I'm slowing down, and do it the right way.
And fatigue has a negative impact on your decision making and your
Exactly.
reflexes and all those things that have to be sharp.
And that gets back to what we talked about earlier. Know which way the wind's blowing. All the time, know which way, and use the wind to your advantage, and you won't be near as fatigued at the end of the day. Trust me, it'll be like, wow, that wasn't a bad day at all. But if you fight the wind all day long, trust me, it's going to show up at the end of the day, and it'll show up in your work too. And you're out there to do a job, and you want to do it as best you can to the best of your ability. So don't be sloppy. Don't be sloppy. Do the best you can.
Steve, there's several different ways to turn an airplane around. Talk to us about the different methods of turning an ag plane around.
Mm-hmm. Well, every pilot does have his favorite pattern that he likes to use. Most of the time, I like to use racetrack patterns. You have
Why is that best?
Because once I set my AB line, I've already looked at the field, so I pretty much already know by the time I set my AB and then I go to the other side of the field to C, I already know when I come around to make my fourth pass that it's going to be dead in the middle of that field. I already know where I'm going to be. So it's back to what I said, plan every pass. While you're on this pass, plan the next pass. Now, I do like a back-to-back if the wind's blowing harder than I'd like, because I'll use the wind to my advantage. I'll turn down and go into the wind, and I'll just chop my way into the wind, especially fertilizing or something like that. I like to, instead of doing a parallel or sometimes I'll do a squeeze, but that's very, very rare. Most of mine are racetrack or back-to-back. Use a quick track every now and then. People that don't use a quick track, that's you put your AB, then you go, you just come around and you set your own line for the C. But the racetrack, you go to the far opposite side of the field and set that line. But I like a racetrack.
And it doesn't require as aggressive of a turnaround maneuver.
It doesn't.
The radius of the turn is the same on every turn, right? So you kind of get into a rhythm, it seems like, with a racetrack.
Exactly. And with the quick track, see, that's the exact opposite of that, because when you pull out of the field, if you made that aggressive turn, when you set the C line, well, that's set in stone. That's what you're going to have to do from the rest of the field. So I don't like that. I like going out and I like setting it up at my pace.
Steve, just round numbers, how many turnarounds would a guy make in a day? 1,000?
If he's in the Delta, obviously, yeah. You could make up to 1,000
turn
turns
around
a day.
1,000 times a day?
You sure could,
Okay.
yeah. Depends on the region you're in, and 40, 50, 60 takeoffs and landings a day on top of that.
And that highlights how important it is that we always kind of preserve our buffer, right? Our margin of safety. This would be a good time to introduce Colonel Mike Mullane. Colonel Mullane is a 3-time Space Shuttle astronaut mission specialist. He's a West Point graduate. He flew combat tour in Vietnam, and he's studied the phenomenon known as normalization of deviance. And he has some great ideas about how that relates to our industry.
Normalization of deviance. That's a strange combination of words. What does it mean? Normalization of deviance is that process in which individuals who operate in hazardous environments, as each of you do, repeatedly violate the line of safety that has been established by their training and procedures. These lines of safety, when we're on the safe side of these lines, we have margin to deal with the unexpected. And in aviation, we all know the unexpected is out there. And what motivates people to step over these lines of safety? It's almost always self-inflicted pressure. For example, you can rationalize that by operating at higher angles of attack and greater G-loads in your turns, you can finish one job quicker and get on to the next job. That will translate into more money at the end of the day. So that's exactly what you do. You successfully operate closer to the stall and end up finishing the jobs quicker and pocketing more money. All appears well. But what this success does is it opens the door to doing it again and again and again until that unsafe behavior is normalized into your air operations. Normalization of deviance. And in fact, you will, in all likelihood, use your success to justify pushing your line of safety deeper into unsafe territory, of eating away at the margin that line of safety has provided you, until at some point the unexpected occurs and you have no margin of safety to deal with it. A bird strike, an obstacle, a shift in the wind, and in that case, a fatal crash is a very real probability. Normalization of deviance has brought grief to countless aviators and astronauts. The 1986 Space Shuttle Challenger disaster, which killed 7 astronauts, including 4 of my astronaut classmates, was a result of a 4-year normalization of deviance process. Challenger was lost because of a failure of an O-ring seal in the right side solid rocket booster that allowed 5,000 degree Fahrenheit gas to penetrate the casing, the steel wall of that booster, and cause the catastrophe. But this O-ring defect was first seen when the boosters were recovered from the second shuttle mission. Challenger was the 25th mission. So the obvious question is, why did flights continue with this known danger? And the answer, schedule pressure. The NASA contractor team was under immense schedule pressure to achieve an impossible goal of a mission approximately every 2 weeks. In other words, just as pressure can motivate you to accept more and more risk in your air operations, pressure motivated the NASA contractor team to accept more and more risk in their space shuttle operations. Eventually, for NASA, the O-ring, the margin of performance, was fatally compromised by the unexpected. Extremely low temperatures on that January morning that Challenger was launching. That super cold temperature stiffened the O-ring, made it impossible to form a seal, and guaranteed that tragedy would result. Challenger is a warning for all of us, and we should take to heart the lessons that can be learned from that tragedy, as well as the lessons that can be learned from the near misses and disasters that have occurred in your air industry. The first lesson is this: risk has no memory. I think as humans we have an incredibly difficult time getting our heads around this. We tend to believe that a risk successfully taken is a risk diminished. It does not work that way. The laws of physics have no memory. I want you to think about this. NASA flew 24 missions before Challenger. On each of those missions, the risk to a catastrophic O-ring failure remained exactly the same. It didn't matter how many times NASA was getting away with it. The risk remained exactly the same for disaster for all of those missions, including my first mission, which was the 12th mission. And the same applies to you. I don't care how many times you've operated close to the stall, the risk of a stall, spin, and fatal crash remain the same. You could have operated razor close to the stall for 1,000 times, 10,000 times, and the risk has never changed. It remains exactly the same for you as it did for us as astronauts in those 24 missions. Risk has no memory. Never be victimized and think that it does. Another lesson: follow your procedures to the letter every single time. They are figuratively written in blood. On the very first day of my aviation training in the Air Force, the instructor held up the checklist and said, "Gentlemen, this document is figuratively written in blood." He said, "You can go back in history and you will find crashes that occurred, crews died, lessons were learned, and these lessons have now been incorporated into these procedures to protect you. Follow your procedures." And the same applies to your procedures. they are certainly figuratively written in blood. You can go back in history and find where tragedy occurred, and those lessons have been learned and put into your procedures to protect you. Follow your procedures every time to the letter. And a final lesson is this: it only takes one safety shortcut to open the door to normalization of deviance. For NASA, the door was opened when flights continued after the near miss of Flight 2. There are numerous instances of O-ring anomalies on subsequent missions, but each time the risk was accepted. Why? Based on the risk rationalizations that had occurred in the past. And the same thing can happen to you. Just one successful flight of risk-taking, of stepping across your line of safety, could open the door for you to do it again and again and again until you're a victim of normalization of deviance. There is no such thing as one and done when it comes to a safety shortcut. The one always leads to more. Don't become a victim of normalization of deviance. Fly safe, fly smart, stay on the right side of your line of safety. Give yourself margin to deal with the unexpected, because I guarantee the unexpected is lurking out there ready to bite you.
Colonel Mullane's message about normalization of deviance is a really powerful message and very applicable to our industry. Steve, let's dig a little deeper into the technical aspects of what's going on when an airplane stalls and when an airplane spins. When we learn about spins, we're taught that an airplane has to be stalled and there has to be a yaw to cause the spin. Now, in an air show routine, usually the pilot causes the yaw with rudder inputs on purpose, right?
Right.
In the ag environment, the spin is very much an unintended maneuver. And that yaw is caused by gyroscopic forces on the propeller or by incorrect flight control inputs.
What actually happens, you can stall an airplane, well, both wings stall. The difference in the spin is one wing is flying and one wing is not flying. And what is the reason for that wing to all of a sudden not fly? Is because of yaw, and it's always with the rudder. If you're pushing on the left rudder, you're going to stall the left wing. If you're pushing on the right rudder, you're going to stall the right wing. And what happens is whenever it goes to break into that spin, you push on the left rudder too much, this wing is actually slower. This wing is actually speeding up. And what happens is as it tends to break, it tends to roll over in its back, because this airplane's doing what its job is. It's producing lift. You've lost all the lift on the bottom wing, and it tends to rotate over onto its back. And we're going to go out and do some of that in the T6, and we're going to really screw up some turns and try to stall it and make it do this exact same thing and recover from that. But air show environment, you're doing it because you've pre-planned it. Airplane's designed for that, and you're showing those aspects of there. In an ag plane, you don't ever want to do that. Ever let it get to that point. But the main thing, to get in a situation, to get into a spin, you have to have loaded the wing. In other words, you have to have some G on the airplane. Well, what's an ag plane? The wings you're constantly loading them. They're always loaded. You're loading that wing. When you're pulling on that wing in that turn, both wings are doing their job. So you need to stay coordinated to keep both wings flying. In the event that something happened, that you were turning on the AB line too much, and you exacerbate the situation by pulling on it and trying to roll the rudder, and it does break. You've literally lost the lift on this wing. This one's going to try to roll you on your back. Now you've got 300 feet to recover, and then we're going to show all that in the T6. We're going to screw up some turns and make people realize how important it is to stay coordinated. Making those left turns riding the inside rudder is nothing you need to be doing. And some people get confused on that stuff. They get in a situation where they can't think straight. Right. If you'll think rudder hardest to push is going to be the right rudder every time. No matter what. Spinning the left, spinning the right, whether you're inverted, whether you're right side up, rudder hardest to push is the correct rudder. Never forget that.
Steve, I could sit around in a hangar and talk about airplanes all day.
Yeah,
You
me
probably
too.
can too. What do you say we go out on the ramp and get in the T6 and go put some of this stuff to practice?
Let's do it. Let's go mess some turns up and see what happens.
Sounds good.
Good deal.
Let's go.
Air is smooth as glass this morning. Oh, this is going to be a nice flight.
Yeah. Perfect morning for an inversion.
Yeah. Yeah. What are you feeling like you want to do first?
I think we'll start out with an AB line.
Okay.
And then we'll do a turn. We're going to simulate what not to do.
Okay, so we'll do an incorrect left turn.
Correct. We're going to, first we're going to set our AB, and then we're going to make an incorrect turn, which would mean we're going to make our initial turn into the wind, which is actually going to feel good at first, but then you're going to pay for it later. So here we go. So here's, we're at 5,000 feet roughly. Got our power set. Alright. I'll turn some smoke on. Alright, get on 5,000. 5,000. Here we go. Pitching out of the field. Coming back around. We're starting to turn downwind. And oh, there she goes.
There it goes.
I rolled it on through. That's how you want to do it. So we lost 200 feet.
That's right. In an ag mission, in an ag environment, we don't have that 200 or 300 feet to play with.
No, not at all. And number two is you're not going to be expecting it. I'm going to do one to the right. And this time, I'm going to try not to roll through. I'm going to try to picture myself trying to just straighten the airplane. All right, here we go. Turn it back to the right. Turn it back to the right. Bam, I hit the ground. You see that?
Sure did, yeah. Every ag pilot needs to do some of that.
They really do. They really do. Especially some of the beginner guys that just never have been in that situation.
I've talked to people before who are kind of afraid of doing that kind of stuff, and I don't know that that's a good thing. I don't know.
It's not a good thing.
The fear of it is probably not a good thing.
It's not. It's really not a good thing. You need to do just what you did, and then you go, I see. And when you see, you recognize. All right, one last time, gear down and locked. Looking good.
A lot of times you hear from people who are uncomfortable with stalls and spins and that sort of thing, and I don't think anybody in our industry ever needs to be uncomfortable with those maneuvers. I think we need to be very comfortable.
I agree.
So maybe during the off season or maybe occasionally during the regular part of your season, it would be a good idea, if you're uncomfortable doing stalls and spins, to get with an instructor who's experienced in aerobatic flight. Find an airplane that's appropriate for practicing and experimenting with those kind of maneuvers.
Totally
and
agree.
I think it's a good idea for everybody in our industry to constantly practice those maneuvers and the recoveries from those maneuvers.
I totally agree. I mean, you need to be comfortable if you're uncomfortable with doing stalls and spin recovery, then there's an issue there that needs to be addressed. So I totally agree with that. Go find an airplane that's certificated for that. And if you're real uncomfortable, find somebody like myself, or if I can, I know a lot of people that can. There's lots of great places that are out there that you can take courses that teach you to where you get that away from you. Because believe it or not, you don't want to be fearful, afraid of something like that, because if you catch a situation like that, you might freeze up. and that's the last thing you want to do.
That's right.
Yeah, that's great advice. If you're uncomfortable, go get some instruction. You know, we all of us as pilots, some of us get bad habits and don't realize it.
Another good point.
Until you go fly with somebody else and he brings it up to you, you go, wow, I was doing that. You know, or vice versa. You might go help him. He might have a bad habit, and between the two of you, get it resolved.
We get rusty and we get complacent, and there's no substitute for knocking the rust off and practicing
Amen.
and doing the things that we don't do every day, right?
Complacency. Let's talk about that. That's the number one pet peeve of mine is complacency. Being an ag pilot for 40 years, an air show pilot, and having a lot of time, I constantly tell myself that don't get complacent. This is just not another air show. This is just not another day of ag flying. Every day when you get strapped in, you need to have your mindset and wrapped around what you're going to be doing that day. Complacency has killed so many excellent, seasoned pilots that let their guard down from complacency. And I guarantee if you could back the clock up and talk to the ones that did, they were like, God, I knew better than that. I knew better than that. So I try to tell myself, you know, being a pilot with over 31,000 hours, hey, Steve, don't let your A game down. You know, don't let your A game down. So every time I strap in, just like we strapped in this morning, I tell myself, okay, A game on. I'll make sure this is right. This is right. Before I go, this is right. This is where we're going to be.
That ties in perfectly with Colonel Mullane's message about risk has no memory. Just because you've gotten away with something 100 times
Right.
doesn't mean that the risk was any less. We also learned how important it is to establish what your own personal safety margins are and to realize why those safety margins exist and to obey them, right? We don't want to step across our safety margin because they're there for a reason.
Totally. Those guidelines are written in stone, and if you don't abide by those guidelines, it's going to catch up with you eventually, you know. And you know, everybody needs to stick with a set of guidelines if you want to be an old pilot one day.
Steve, I sure had a good time flying with you this morning. I feel like we had a lot of fun and we learned a lot.
Me too. You did a good job.
To me, the three takeaways from today are to choose your turnaround that's appropriate for the mission, pay attention to your margin of safety, and don't ever step across it.
Always.
And smooth and steady is the best way to fly these airplanes.
Amen, brother. Hey, let the airplane do the work. I had an old timer tell me one time when I first started, he said, "What's the most important thing about flying ag, Steve?" And I said, "I don't know, Mr. Charlie, what?" He goes, "Hooking the loading hose up." He said, "Son, if you can't hook that loading hose up, you're having a bad day if you can't hook it back up." Keep that in mind whenever you're flying and you find yourself in a situation that you don't like. Wings level, go around. This airplane does 140 miles an hour. You'll be back before long. You'll be right back. You'll never miss it. Never miss it.
Great advice. Steve, I had a good time today. Thank you for coming out. The weather was perfect. I think we had a great time. Learned a lot.
Heck yeah, you did a great job. I enjoyed it. That was a nice flight, wasn't it?
That was a lot of fun.
Really
Thanks
nice.
for that.
Yes, sir. I enjoyed it. Thank you for having me. We had a ball, didn't we?
Yes, we did. Thanks for the flight.
You're welcome. Thank you for having me, Mike.